NASA unveiled pictures from a new space telescope capturing the deepest images of the universe anyone has ever seen.
The James Webb Space Telescope just detected a terrifying bubble stretching across the void, a vast, shimmering cavity in the interstellar medium that defies everything we thought we knew about the structure of the cosmos. It appeared first as a subtle dimming in the infrared survey data, a barely perceptible void against the tapestry of glowing nebulae and distant galaxies. As the telescope's instruments focused, the bubble revealed itself in all its unsettling grandeur, a spherical shell of ionized gas hundreds of light years across, its edges glowing with an otherworldly phosphorescence born of shock-heated plasma. The discovery sent ripples through the astronomical community, for such a structure, so immense, so sharply defined, should not exist in a medium governed by gradual diffusion and the slow dance of stellar winds. Its very presence hints at forces at work on scales and energies unimaginable, an echo of cosmic events that have shaped the universe in silence and shadow. Before we start, hit the like and subscribe buttons for more exclusive news. At first glance, the bubble seems to be an empty cavity carved out of the surrounding interstellar clouds, its walls a spectacular ring of radiant gas and dust. Infrared spectroscopy reveals that the gas is heated to millions of degrees, ionized by a torrent of high-energy particles and radiation. Yet there is no central star or cluster powerful enough to have driven such an excavation. No supernova remnant appears at its heart, no glowing pulsar, nor black hole jet. Instead, the bubble hovers, suspended in a cosmic void, an orphaned testament to a cataclysm that left no smoking gun. Its sharp boundaries suggest a sudden, violent event, one that blasted material outward with furious force. Yet that same evidence is matched by a serene symmetry, as if the universe itself had paused to admire the perfect sphere before moving on. The dimensions of the bubble are staggering. It spans nearly 1,000 light years from rim to rim, dwarfing even the largest known superbubbles carved by successive generations of supernovae in the Milky Way. Its walls glimmer with emission lines of highly ionized oxygen and neon, and the characteristic signatures of dust grains shattered by shock waves. The density contrast between its interior and exterior is immense. Within the cavity, gas is so rarefied that infrared emission is almost entirely absent, while just beyond its walls lies a tapestry of molecular clouds, ripe with star-forming potential. That stark boundary is a puzzle, for shock fronts traveling through such tenuous media should dissipate over time, smoothing into oblivion. Yet here, the bubble's shell remains razor-thin, a cosmic scar preserved against the eroding tides of interstellar turbulence. Spectral analysis has uncovered anomalies that deepen the mystery. The gas in the bubble's walls exhibits Doppler shifts indicating expansion speeds of over 1,000 kilometers per second. That velocity far exceeds the expectations for any known stellar explosion in such an environment, suggesting an energy release orders of magnitude higher than a standard supernova. Moreover, the bubble's age, as inferred from the expansion rate and current size, is reckoned to be only a few thousand years, a blink in cosmic time. Where then did this colossal outburst originate? No records of a bright supernova in a nearby galaxy correspond to that time frame. No gamma-ray burst catalogs list an event of such ferocity in that region of the sky. It is as though the bubble sprang into existence without fanfare, its creator unseen. The ridge of the bubble's shell is not uniform. Observations reveal filamentary structures and knots of denser gas, like chiseled pillars held in suspension along its rim. These filaments bear the telltale scars of magnetic field interactions, twisted and stretched by forces that defy simplistic hydrodynamic models. Magnetohydrodynamic simulations struggle to reproduce features so intricate and coherent at such vast scales. It suggests that the instigator of this bubble was not merely mechanical but entwined with the cosmic magnetic web, an unseen architect leveraging fields that twist across intergalactic distances. The result is a mosaic of glowing arcs and sinewy strands, each pointing back toward the silent void at the center. The bubble's existence carries profound implications for our understanding of cosmic evolution. If such structures can form without obvious progenitors, then the interstellar medium must conceal processes far more exotic than the death throes of massive stars. Could it be that a previously unrecognized class of explosive event lurks in the darkness? One powered not by nuclear fusion but by the sudden release of gravitational or magnetic energy on titanic scales? Perhaps the collapse of a primordial black hole or the interaction of dark matter clumps produced a detonation unparalleled in its ferocity. Such possibilities force a reckoning with the very building blocks of cosmology, demanding that we revisit models of how energy and matter interplay across the vast voids between stars. Dark energy, the mysterious force accelerating the universe's expansion, may also play a role in this drama. While often considered uniform and gentle, could dark energy fluctuate locally, pouring forth in bursts that puncture the interstellar medium with violent shockwaves? If pockets of dark energy surge through the galaxy, they might inflate bubbles of sheer emptiness, leaving only the compressed shells of gas to mark their passage. This notion challenges the prevailing view of dark energy as a uniform backdrop, suggesting instead that it may interact in subtle, transient ways with ordinary matter. The telescopic detection of such a bubble compels astrophysicists to consider such speculative but tantalizing hypotheses. The bubble's thermal profile further bewilders. Temperatures within the shell approach several million degrees Kelvin, hotter even than many young supernova remnants. Yet the emission spectrum lacks the high-energy X-rays typical of such environments. Instead, it glows primarily in infrared and radio frequencies. This divergence implies that the bubble's heating mechanism is not simply thermal shock, but involves particle acceleration processes more akin to the cosmic rays that pervade the galaxy. Could the bubble be a reservoir of accelerated particles? A cosmic ray accelerator on an unimaginable scale? If so, its discovery offers an unprecedented laboratory for studying the origins of high-energy particles that bombard Earth and may have shaped the habitability of planetary systems. Equally intriguing is the bubble's influence on surrounding star formation. Molecular cloud cores lying just beyond its shell show signs of collapse, their densities elevated and temperatures spiking under the bubble's pressure. The event that created the bubble may have injected turbulence into nearby clouds, triggering a burst of starbirth in its wake. This process mirrors theories of triggered star formation, where shock waves compress gas to the tipping point of gravity. Yet the scale here is colossal. Entire stellar clusters could arise from the fallout of this single cosmic blow. In that sense, the bubble is both destroyer and creator, a force that cleared the canvas only to seed new masterpieces of stellar evolution. The ramifications extend to galactic ecology at large. If such bubbles can form spontaneously or via unknown mechanisms, they could serve as cosmic engines, reshaping the structure of galactic disks and cycles of star formation. They might carve out vast chimneys through which galactic winds escape, contribute to the enrichment of the intergalactic medium, or even influence the distribution of magnetic fields on cosmic scales. The discovery prompts a re-examination of the feedback loops that govern how galaxies grow and evolve, suggesting that we have only scratched the surface of the universe's capacity for self-organization and change. Observationally, the bubble challenges the limits of our telescopes. Its detection was only possible thanks to Webb's unprecedented sensitivity to infrared wavelengths, which can pierce through clouds of dust that would obscure more conventional telescopes. The bubble's shell, thin and faint invisible light, shines in the longer wavelengths as dust grains heated by shock waves radiate efficiently. Without Webb's cryogenically cooled instruments, the bubble would remain hidden, a silent void in the cosmic tapestry. This underscores the necessity of pushing our technological frontiers ever further, for who knows what other wonders and terrors lie concealed beyond the veil of light. Theoretical astrophysicists now race to build models that can replicate the bubble's formation and evolution. Early attempts couple magnetohydrodynamics with exotic dark matter candidates, but no single framework yet captures all observed features. Some propose that the bubble is the fossil of a gamma-ray burst that occurred centuries ago. Its electromagnetic signature long faded, but its mechanical impact still expanding. Others suggest a merger of two neutron stars deep within the spiral arm, an event so cataclysmic that it hollowed out the surrounding medium. Yet the absence of heavy element enrichment in the bubble's shell argues against these nucleosynthesis-rich scenarios. The truth may lie in a novel phenomenon awaiting its theoretical moment of birth. If you like this video, please give it a like and subscribe to our channel. Also, could you leave your comments below and tell us, what are your thoughts on the terrifying bubble James Webb just detected? Predictions? We want to hear from you. Thank you for watching and see you next time.